Hi, everyone. Let's start Chapter 1 on General Function Theory. And we're going to start with Section 1.1 with an introduction to functions. We'll go through the first part of it very quickly. A function is a special type of relation, which is a set of ordered pairs of the form input, comma, output. We can think of the inputs as x-coordinates and the outputs as y-coordinates. So, for example, here's a relation, a set of ordered pairs. This relation maps, for example, the input 1 to the output 5, and so forth. Now, a function has the special property that each input yields exactly one output. So we are not allowed to have the following happen. We are not allowed to have one input yielding two or more outputs. In other words, we cannot have a single x-coordinate yielding two or more y-coordinates. That is illegal for a function. It's not illegal for a relation in general, but it's illegal for a function. And by the way, something like this could be the graph of a relation, but it could not be the graph of a function. It violates the vertical line test. So a function is a special kind of relation where this is not allowed, an x yielding two or more y's. The domain of a function is the set of all input values. It's like the set of all first or x coordinates. The range of a function is the set of all the resulting outputs. It's the set of all the second or y coordinates. So we associate the domain with the set of x coordinates we pick up and the range with the resulting set of y coordinates we pick up in the usual setup. So let's go to this over here. The expression f of x is read as f of x or f at x. It does not mean f times x. So f of x represents a function value that results from an input value x. Here, for f of x, x can be thought of as an input value or the argument of f. So x here represents the input or the argument for the function f. And we can think of a function as a kind of input-output machine, kind of like a calculator button on your calculator, like square root or x squared, the squaring function. So when we evaluate a function at its input, we're determining the resulting output. And we express it in simplified form. A function is defined, or it exists, only on its domain, only for those values of x in the domain of f. If x is not in the domain of f, then f of x is undefined, or it does not exist. A function rule describes how a function assigns an output to an input. So something like this, f of x equals x squared. This tells us to take the input or argument x and square it to get the resulting output, the function value. Let's talk more about this squaring function. And this corresponds to the x squared button on your calculator. The domain is assumed to be the set of all real numbers. We can square any real number. So we're defining the function f by this rule, f of x equals x squared. The domain is assumed to be R. Now bear in mind that we could have just as easily defined this rule as f of u equals u squared. Please say f of u. Either way, f squares its input. I could say that f of grandma equals grandma squared. So if f is the squaring function, remember f is the function. If f is the squaring function, what is the value of f of negative 3? Evaluate this. Be careful. When you substitute in the negative 3 for x, remember to put grouping symbols. Always be prepared to put grouping symbols whenever you're substituting or plugging in. Don't forget to put grouping symbols around the -3 when you square it. The square of -3 is +9, not -9. If you write this without grouping symbols, this is -9, but this whole thing is wrong. The function value at -3 is +9. This is what the input-output machine does. If you put in -3 in your calculator as the input or argument, when you press the x square button, which represents a squaring function, the output is +9. Now, we often classify functions based on the type of rule it corresponds to. For example, f is a polynomial function if we can define it as f of x equals a polynomial expression in x, like x squared plus 1, for example. And we can say similar things about rational functions and algebraic functions. So down here, for example, this is the defining rule for a polynomial function. This is the defining rule for a rational function, where we allow for fractions of polynomials. And this is a defining rule for an algebraic function in general, where we allow for things like rational exponents on x and square roots and cube roots and so forth of variable radicands. Remember, all polynomial functions are rational and all rational functions are algebraic. Next, various ways that we can represent functions, aside from a defining rule or formula.